In this video, we're going to look at Gauss Law and electrical potential. In the previous video, we talked about Coulomb's Law, and the Coulomb's Law, as we know it, we can also express it in the form known as Gauss Law. On its own, the determination of electric field using Gauss Law is really not difficult. It's just that the number of problems we can solve using Gauss Law is quite limited. The reason for that is because the charge distributions must have special symmetry properties. Now, one of the importance of Gauss Law really is not on how beautiful or how simple it is. Rather, it is on the importance, the insight, the additional nature that it gives us into electrostatic fields. Okay, but before we go into Gauss Law proper, let's just look at electric flux. We use the symbol phi to denote electric flux. Now, phi on its own is given as charge Q, capital Q, over permittivity of free space. Now, you can also represent phi as electric field times area cos theta, the angle. So let's look at an example. So if you look at this question, it says, at each point on the flat rectangular surface shown below, the electric field has a magnitude of 350 Newton per Coulomb and makes an angle of 50 degrees with the normal. Calculate the electric flux for this surface. Now this is the drawing, the sketch. Now this is a rectangle. On this rectangle, for us to get the area, remember that flux psi or phi is given as EA cos theta. Theta is the angle that it makes with the normal. This is the area of the rectangle. Of course, now the magnitude of that electrical field is 350 Newton per Coulomb. Area of that rectangle A can be given as length times breadth, which is 20 cm times 15 cm, which will give you 300. So that 300 centimeter cubed, if we convert it to meter cubed, we're going to have 3 times 10 raised to power minus 2 meter squared. I beg your pardon. Now, having gotten this, of course, we know that the angle is 50 degrees. All we need to do is to plug in into the above equation. Phi or psi is equal to E, which is 350, times the area, which is 3 times 10 raised to power minus 2 meter squared, times the degree, which is cos 50. So if we can resolve cos 50, we have 350 times 3 times 10 raised to power minus 2, and cos 50 is 0.64 thereabouts, if I'm correct. Then if we multiply throughout, we will get 6.72 Newton meter squared per Coulomb. That is the electric flux. Now, if we look at Gauss Law, Gauss Law states that the surface integral to the normal component of an electric field through any closed surface containing a total charge, capital Q, is given as Q over x 0. It's given as Q over x 0. That's what Gauss Law says. Now, if we look at the applications of this Gauss Law, if you look at the first application, is that we use it in electric field due to a charged spherical conductor. So in that case, the electric flux is giving us 4 pi r squared E. And you know that E, we have 4 pi r squared. You know that E, according to Coulomb's law, it says that E is, let's say, multiplied by E. So we represent E with Q over 4 pi S00 r squared E. So this is Q over E naught. The second application is in electric field due to a plane sheet of charge. So the third application is what I mean by number two is we have a plane sheet of charge where you have something like this, a plane sheet of charge. Number three, so the third application is electric field due to a charged cylinder. That's by Gauss law, where you have 2 pi L E is equal to Q over E naught. So